Let's unpack this. Welcome everyone to a deep dive that might just change how you think about something seemingly simple. Charging your electric vehicle at home.
Yeah, it feels straightforward, doesn't it? Get the car, call an electrician, install the big powerful
You
charger.
raptly. You've probably pictured that whole process, but well, maybe that's not the whole story.
Right. We're digging into some insights today from a YouTube video from Technology Connections. It's got this great title. Something like, "The standard car charger is usually overkill, but your electrician might not know that."
Huh. Yeah, kind of provocative. And that's our mission for this deep dive, really. We want to explore why that standard, high-power charger might be way more than you actually need.
And crucially, what the alternatives are. Simpler, cheaper alternative that might be a perfect fit based on how EV charging actually fundamentally works.
So let's start with that standard assumption. Where does it come from? If you look online or maybe talk to someone who's installed one?
You'll almost certainly hear about the NEMA 1450 receptacle. It's a 50-amp circuit, usually.
Right, 50 amps. And that typically translates to, what, about 9.6 kilowatts of power delivery from the charging station?
Yeah, around that. 9.6 kilowatts. And look, that sounds great on paper. More power, faster charging.
Who wouldn't want faster charging? But the Technology Connections video really pushes back on this hard.
It does. The core argument is, well, that much power is usually massive overkill. Unless you're doing some serious daily mileage.
Like, what do they say? 200 miles or more?
Yeah, something like that. Every single day in, day out. Which, let's be honest.
That's not most people's commute. Not even close for many.
Right. So why is the 1450, the 9.6 kilowatt setup, so often recommended then? The video suggests, well, maybe it's just the easy answer for electricians.
A known quantity. A one-size-fits-all sort of thing.
Kind of. And, I mean, if your house's electrical service can handle it easily and the wiring run isn't too bad, it is nice to have that top-end capacity, sure. No denying that.
But that's a big if for a lot of homes, isn't it? Running a brand new 50-amp circuit, that can be complicated and expensive.
Oh, definitely. Especially if it's a long run or has to go through finished walls or whatever. And then there's the panel capacity itself.
You mean your main electrical panel might not even have enough juice left?
Exactly.
Yeah.
Adding a continuous load like an EV charger. And remember, code usually limits you to 80% of the breaker. So 40 amps continuous on a 50-amp circuit, that might push your whole home's service over the limit.
Which means a service upgrade for the whole house.
Potentially, yeah. And that can get really expensive. We're talking thousands sometimes.
Yikes, okay. And what about installations outside a garage? Is that NEMA 1450 plug ideal for, like, being out in the rain?
Well, it's generally not considered the most robust solution for outdoors. Those purpose-built, hardwired charging stations are often better sealed against the weather. So the 1450 isn't always the answer there either.
Okay, so the standard route has potential cost and complexity issues, which brings us to what you call the aha moment from the video, the flexibility aspect.
Yes, this is the absolute core of it. This is the game changer. The video makes it crystal clear. EV charging equipment, the proper term, is EVSE, electric vehicle supply equipment.
Yeah.
It's not locked into only working on big 50-amp circuits.
So you can put it on smaller circuits.
Absolutely. It can be installed on a branch circuit of pretty much any reasonable size. You match the circuit to the power you actually need, or, maybe more importantly, what's easy and affordable to install.
But wait, how does that work? I thought, you buy a 40-amp charger or a 48-amp charger. Isn't the hardware fixed?
Good question. That's where this concept of field commissioning comes in. Many modern EVSEs are designed so they can be configured after installation.
Configured how?
Often it's surprisingly simple. Like the video showed an example using little internal DIP switches. You literally flip switches inside the unit to tell it, hey, you're connected to a 30-amp circuit, or you're on a 20-amp circuit, or whatever it is.
So you're setting a limit on the EVSE itself to match the wiring.
Exactly. You're telling it the maximum capacity of the circuit it's plugged into or hardwired to.
Okay, wow. So what does this actually mean for, for someone listening who's planning their setup?
It means you suddenly have way more options. You're not automatically locked into that big, potentially expensive 50-amp circuit install.
You could maybe use a smaller circuit, one that's easier to run, cheaper materials.
Precisely. Maybe it avoids needing that massive service upgrade, or avoids tearing up your walls, or allows for an easier outdoor run. It opens up so many possibilities that are less disruptive and, frankly, less costly.
Okay, to really get why this works safely, the video breaks down a common misunderstanding. The box on the wall. it's not actually the charger, is it?
Correct. That's a key distinction. What we call the charger, the EVSE isn't charging the battery directly. The actual battery charger is inside the car.
Inside the car. Huh. So what does the EVSE do then?
Think of it like a smart, heavy-duty extension cord with communication skills. Its main jobs are safety, making sure the connection is good, and signaling.
Signaling what?
It sends a simple signal to the car. Basically, hi, I'm an EVSE. This circuit I'm connected to can safely provide a maximum of, say, 24 amps continuously.
Right.
Or 16 amps or 32 amps, whatever it's been configured for.
And the car receives this signal.
Right. And the car's onboard charger then takes the AC power from the wall, converts it to DC for the battery, and importantly, it draws only up to the maximum current level that the EVSE signaled was available.
So the car is the device actually deciding how much power to pull based on the limit set by the EVSE.
Exactly. The car is the electrical load. It respects the limit set by the supply equipment.
This is blowing my mind a little. So let's say I install a fancy EVSE that could deliver 48 amps. But I only have wiring for a 30-amp circuit, so I use those little DIP switches to tell the EVSE it can only supply 24 amps continuous. Even if my car could accept, say, 40 amps, it will only pull 24.
That's precisely how it works. The car's onboard charger obeys the signal from the EVSE. It will limit itself to 24 amps in that scenario, ensuring the 30-amp circuit you installed is never overloaded.
That's actually really elegant and safe.
It is. It's designed to be safe. And, what if the car malfunctioned and tried to pull more anyway?
Yeah, what happens then?
Two things. First, the EVSE itself is monitoring the current. If it detects the car pulling more than the signaled limit, it'll flag a fault and cut the power. Pow. De-energized.
Oh, okay.
And second, you always have the circuit breaker in your panel as the ultimate backup. It'll trip if there's a sustained overcurrent. So yeah, like the video says, don't overthink this. The system has multiple layers of safety built in.
Let's make this concrete. The video gave a great real-world example, right? The install at the speaker's parents' house.
Yeah, for their Chevy Bolt.
Yeah.
And it perfectly illustrates this flexibility. They didn't go for the big 50-amp circuit.
What did they use instead?
They installed a 30-amp circuit. The video mentioned this was partly due to the type of cable they used, 10-gauge MZ cable, which influenced the circuit size choice for their specific situation.
Okay, 30 amps. And applying that 80% rule for continuous loads.
That means a maximum continuous draw of 24 amps.
And 24 amps at 240 volts is carry the one.
They're about 5.8 kilowatts.
Yes, exactly. 5.8 kilowatts. Compare that to the 9.6 kilowatts from the standard 1450 setup.
So significantly less power on paper. How did it actually work out? Was it painfully slow?
This is the kicker. According to the video, the answer was a resounding no. It was absolutely fine. They actually bought an EVSE capable of higher power, a Grizzly Classic, I think it was, rated for 48 continuous.
But they configured it down?
Yep. Used those internal DIP switches to limit it to 24 amps to match their 30-amp circuit. And the install itself. Materials were apparently around $200, and it was like an afternoon project. Their house layout helped, but the point was the scope of work was much smaller.
Okay, but the performance, that 5.8 kilowatt speed for the Chevy Bolt, the video creator was very clear. It has never felt too slow for their parents' needs.
Never. Really?
Never. Now, okay, if the Bolt's battery was completely dead flat empty, it might take about 13 hours to charge fully at 5.8 kilowatt-hours, which sounds long.
Yeah, that sounds like a long time.
But how often do you arrive home with a totally empty battery? Almost never, right? You plug in with maybe half charge or 30% or whatever.
Right, you're just topping up what you used that day.
Exactly. And in their typical use case, plugging in when partially charged, the car is usually full or back up to their target charge level in about 8 hours.
8 hours. So perfect for an overnight charge while you sleep.
Totally. Plug in when you get home from work, unplug when you leave in the morning. It's ready to go.
And the video even mentioned testing it with a car with a bigger battery.
Yeah, the creator's own Hyundai Ioniq 5. Even with its larger battery, that same 5.8 kilowatt charger could add about half the battery's capacity, roughly 80 to 120 miles of range in about 7.5 hours.
Wow. Okay, that really changes the perspective. Adding 80, 100, 120 miles overnight
is more than enough for the vast majority of people's daily driving. Even a pretty long commute, like 50 or 60 miles round trip. You replenish that easily overnight at 5.8 kilowatts.
You're not trying to do a full 0 to 100% charge every single night.
Precisely. That's the key mental shift the video emphasizes. You don't fill your gas tank every day, Rennie. You don't need to fill your EV battery every night either. Just put back what you used. And for most daily driving, 5.8 kilowatts or maybe even less is plenty.
So these smaller circuits are totally viable. What other, maybe overlooked charging options did the video bring up?
Well, it's always good to remember the baseline, level 1 charging.
Just plugging into a regular wall outlet,
Yeah.
120 volts.
Every EV can do it. Most come with a cable. It is slow, no doubt. Maybe adds like 40 miles of range overnight if you're plugged in for 12 hours or so.
Which sounds glacial.
It is. But hey, if your daily drive is only 10 to 15 miles, or you work from home those days, level 1 might actually be perfectly adequate, and it costs nothing to install assuming you have an outlet near where you park.
That's a fair point. What about using outlets that might already be there?
Yeah, the video made a great suggestion. Look for existing 240V outlets. The classic example is an electric clothes dryer outlet, often near the garage.
Those are usually 30 amps, right?
Often, yeah. NEMA 1030 or 1430. And there are code-compliant splitter boxes, sometimes called outlet shares,
Yeah.
that let you safely plug both your dryer and your EVSE into the same outlet. Not simultaneously, obviously, but it switches between them.
So you could potentially avoid running any new wires at all.
Potentially, yeah. If you have the right outlet in the right place, it's a huge cost saver.
And for people without garages, driveways, carports.
Big point in the video. Many EVSEs are specifically rated for outdoor installation. They're weatherproof, so you don't need a garage.
Running power along the outside of the house might be simpler sometimes.
Could be, yeah. Lots more flexibility than people might assume.
And of course, for those rare times, you need a really fast charge on the road.
There's the public DC fast charging network. It's growing. It's essential for road trips or emergencies. But the video argues, and I think rightly, that relying on DC fast charging for your daily needs is just not ideal.
Huh?
It's more expensive and less convenient than waking up to a charged car every morning.
Okay, let's circle back to installation for a sec. The video mentioned the issue of melting plugs and outlets, specifically the NEMA 1450 ones you see discussed online. Why does that happen if it's the standard?
Yeah, it's a significant concern. The video points to a few likely culprits. One is just the quality of the receptacle itself.
Like cheap hardware.
Pretty much. Some basic residential-grade 1450 outlets might not be built for the stress of handling a high, continuous load like EV charging for hours every single night. They might be fine for an oven that gets plugged in once or a dryer that cycles on and off, but maybe not this demanding use case.
And installation matters, I assume.
Hugely. Improperly torqued connections, especially with aluminum wiring if that's involved, or even just slightly loose connections on copper. That creates resistance. Resistance creates heat. Heat under continuous high load leads to melting and failure over time.
So if someone does use a plug-in 1450 setup, what's the advice?
The video suggests, first, if possible, just leave the EVSE plugged in all the time. Don't constantly insert and remove the plug, which can wear out the contacts.
Makes sense.
And second, periodically check the plug's temperature after it's been charging for an hour or two. Just carefully touch the plug body. If it feels noticeably hot, not just warm, but hot, that's a red flag. There's likely a bad connection or a failing receptacle, and you need an electrician to check it out ASAP.
Which kind of makes hardwiring the EVSE directly seem like a safer bet, doesn't it? No plug or receptacle to fail.
It definitely can be. Hardwiring eliminates that potential weak point entirely. And it can sometimes make code compliance easier too, especially with things like GFCI protection requirements in garages, as many hardwired units have GFCI built in.
And that 80% rule is key here too.
Yes.
A properly installed 1450 circuit is meant for 40 amps continuous.
Correct. The video speculated that maybe some failures happen if people try to set their charger higher than that, like trying to pull 48 amps, which needs a 60 amp circuit. From a 50 amp circuit, you just can't push circuits beyond their continuous rating safely.
The video also had some opinions on smart versus dumb charging stations.
Huh. Yeah, a little bit of rant there. But the core point was pretty logical, I thought.
Which was?
That a lot of the features marketed in fancy, expensive, smart EVSEs, things like setting charging schedules, tracking your energy use, maybe even remotely limiting the current.
Yeah.
Your car can probably already do all of that through its own infotainment system or the manufacturer's app.
So adding those features to the EVSE itself is just adding complexity and cost and potential points of failure.
That was exactly the argument.
Yeah.
The EVSE's fundamental job is pretty simple. Safely deliver power and signal the limit. More bells and whistles mean more things that can break or glitch. For your own private charger at home, reliability is king.
So focus on a solid, reliable unit.
Yeah. One feature the video did praise as genuinely useful is auto reset capability. If it encounters a temporary grid fault or something, it tries again later automatically. But beyond that, maybe simpler is better for home use. Just needs to be well built and let you configure the current limit to match your circuit.
Okay, let's zoom out a bit, thinking bigger picture. What about the huge challenge of charging for people who don't have a dedicated driveway or garage? Renters, apartment dwellers, condo owners.
This is critical. The video touches on this, and it's a massive hurdle for widespread EV adoption. Getting power to parking spots and multi-unit dwellings, figuring out billing. It's complex.
And the video had a strong take on the common proposed solution of just building more public fast chargers for these folks.
Yeah, it was pretty blunt. The video called relying only on public DC fast charging for residents stupid.
Stupid what?
Because it forces people into a worse user experience. It means constantly having to go somewhere specific and wait, even if it's only 20 or 30 minutes, just to do your regular refueling. It completely misses the main convenience benefit of EVs, which is charging while the car is parked anyway, typically overnight.
While you're sleeping or working.
Exactly. And from an infrastructure cost perspective,
Big difference.
huge. The video states that deploying level 2 AC charging infrastructure, the slower kind we've been talking about, is orders of magnitude cheaper than building out high-powered DC fast charging stations.
So the argument is lean into AC charging. Make that ubiquitous where cars park for long periods.
That's the message. Focus on making simple, affordable AC charging available in apartment complexes, workplaces, street parking, etc. That's seen as the key to unlocking EV ownership for everyone, not just homeowners. It leverages the difference between EVs and gas cars instead of just trying to replicate the gas station model.
One last technical bit from the video. Connectors. The J1772 standard versus the NACS, or Tesla, connector that seems to be taking over. Does it really matter for home charging right now?
The video's perspective was pretty pragmatic. For level 2 AC home charging today, it hardly matters.
Why not?
Adapters. Yep. Good quality, reliable adapters are cheap and readily available. You can easily connect a J1772 charger to a NACS car, or vice versa. So while maybe long-term, NACS is the future.
If you find a great deal on a J1772 charger now, it's perfectly fine to just use an adapter.
Absolutely. Don't let the plug type be a major barrier for home charging right now. It's easily solvable.
Okay, so wrapping this all up, the core takeaway from the Technology Connections video, the central theme of this deep dive, is really challenging that default assumption.
Yeah, that high-power, potentially expensive standard EV home charger. It's very often just not necessary for most people's daily driving.
Instead, simpler, cheaper, easier to install circuits, maybe giving you 5.8 kilowatts or maybe even less, can be totally sufficient.
Because you leverage that long overnight dwell time.
Oh.
You put back the miles you used while you sleep.
So the encouragement for you listening is to really think about your specific situation, your actual daily mileage, your home's electrical setup, your budget.
Don't just assume you need the biggest and fastest option.
Yeah.
Consider what's actually good enough, because good enough might be perfect and save you a lot of hassle and money.
It reframes the whole idea of convenience, doesn't it? From fastest possible charge to effortless charge while I'm doing something else.
Exactly. It's about fitting the charging into your life, not structuring your life around the charging.
So here's maybe a final thought to leave you with, something to chew on. If relatively low power, affordable AC charging is actually sufficient for the vast majority of daily driving, how should that change our approach to the massive challenge of providing charging access everywhere, in apartment buildings, at workplaces, on city streets?
If the solution doesn't always have to be the most powerful, most expensive option, what new possibilities does that open up for making EVs accessible to truly everyone?
Lots to think about there. Thanks for joining us on this deep dive.
Yeah, hope this was helpful. Remember, sometimes good enough isn't just adequate. It might actually be the smarter, simpler, more affordable fit for your EV life.
Definitely take a moment to consider your own driving habits. How many miles do you really need to add back overnight? Is it 40? 80? More?
Keep exploring, keep learning. Maybe dig into the specs of different EVSEs, see how they can be configured, or talk to an electrician about the feasibility of smaller circuits in your home. Thanks for listening.